My MSc from IIT Madras. I pursued my PhD from Usman University. I would like to introduce the notion of real analysis. What are the basic topics in real analysis? Is that set theory and functions, right? Countable, uncountable. So what are the main topics in real analysis? It is started with the sets and relations and functions and by so types of functions you have there and countability, uncountability, and sequences, series, and limits of a sequence, and types of sequences we have seen. We'll see types of sequence means different types of sequence: oscillate, finite, oscillate, infinite, and convergent sequence and divergent sequence, right? Next is what limit of a function. Limit of a function, in defining the limit of a function, we'll see, does it have a continuity and differentiability,
integration,
and Riemann Stieltjes integration and Riemann integration, and sequences, series of functions, sequence of functions and series of functions. And the sequence of functions, we'll see what is the relation between sequence of functions and differentiability. What is the difference the relation between sequence of functions and Riemann integration? What is the difference? What is the relation between sequence of functions and continuity? And we'll see the conditions, right? So these are the major topics in real analysis. Okay, so let me introduce the notion of set theory. So what is meant by set? Anybody?
collection of
well-defined objects is called set.
A collection of
well-defined objects.
collection of well-defined objects. What do you mean by well-defined?
Who are belonging or not belonging.
Yeah. That means a particular object, whether it belongs to the given collection or not, you need to say in a position to say that a particular object, whether it belongs to the given set or not. Understand? You can, you are in a position to say that, to say whether particular object belongs to given collection or not. If such a collection is possible, we can say that the collection is well defined. Otherwise, it's not well defined, right? Means what? Suppose we take an example, a collection of good batsmen or good books in a library. Is it a well-defined collection?
No.
Right? According to me, I like real analysis and matrix theory and matrices and linear algebra, right? Complex analysis. According to your perception, you like, ordinary differential equations, partial differential equation, real analysis. So according to each person, it varies, right? According to each person, it varies. According to my perception, my collection is different. According to your perception, your good books are different. So therefore, this is not my well-defined collection. So it's not a set. Right? A collection of, good persons in India. Suppose if I write a statement like this, is it a well-defined collection?
No, no.
No. Right? According to myself, I like my maths gurus who taught me very well in IIT Madras. According to your perception, you like different persons, right? In mathematics, in different areas, right? So this is not my well-defined collection, right? Suppose a set of all, not set, suppose you take a collection. Collection of natural numbers.
Yes, sir.
Right. Collection of natural numbers. Is it a well-defined collection? Yes. In anywhere, natural numbers are same, right? 1, 2, 3, 4, going on, going on. In anywhere, in India, in abroad, anywhere, natural numbers are same. Therefore, it is a well-defined collection. Therefore, we can say that it's a set. Right? Suppose if I give a restriction on this particular collection, a collection of natural numbers which are less than 20. Is it a well-defined collection? Yeah.
Yes.
Yes.
Yes, sir.
So anywhere natural numbers which are less than 20 always same. For any person, it is same. So therefore, this is my well-defined collection. So therefore, well-defined, now you can understand that what is meant by well-defined. You can say that actually. You can say that automatically whether the particular object, whatever you take, that belongs to the given collection or not. If that happens, the given collection is a well-defined collection, right? So generally, you know that in basic set theory, generally sets are denoted by capital letters. Like A, B, C, like P, Q, R, etc. And the members in a set are nothing but elements. Members in a set are nothing but what? Elements, which is simply called it as an elements, right? Called elements, which are denoted by the small letters. You know that in basic set theory, right? So this is nothing but about set, right? A set is nothing but what? A collection of well-defined objects which are denoted by the capital letters, and elements, we are going to write the elements with the small letters. We represent the elements in a set is nothing but small letters, which we call it as A, B, C, like that going on, right? And once you have a set, suppose you have a like this. Suppose you can have a set of all natural numbers. Set of all natural numbers. Write the set of natural numbers. Is it possible to write a natural numbers? No, right? So therefore, we need to represent a set in two methods. See, set of natural number. Can you write a set of natural number, total natural numbers? No, right? The coordinate is left net, right? So therefore, in such a situation, we represent sets in two types, two ways. One is roster form. This is called as a tabular form, or else set builder form. Set builder form. In roster form, what you do generally, what do you remember roster form? Just writing the elements by commas, writing the elements by ABC, small letter ABC, like, and separating them by commas. Them by commas. Right, enclosed by the flower bracket. Closed by the flower bracket. So, for example, you can take suppose let me take an example. Set of all naturals, which is set of all naturals, which is bigger than 2 and less than 5 and less than 5. That means what? That means what are the natural numbers which are bigger than 2? You know, this is nothing but my set of all natural numbers. Right? This is nothing but what? Set of natural numbers. Right? So which are less than, which is bigger than 2 and less than, this is nothing but counting numbers, natural numbers. 1, 2, 3, 4, 5, going 6, going on. So bigger than 2 and less than 5. What is that? So in my set is,
4.
yeah, 3, 4.
3, 4.
That's it. 3, 4. That's it. So therefore, we write the elements 3, 4 by, like this, and separating them by commas and enclosed by the flower brackets. So this we call it as actually what? Roster form of the particular set. What is my set? A set of all natural numbers lying between 2 and 5. Lying between 2 and 5. Therefore, the elements which are particularly 3 and 4. So we write the elements 3, 4 by, like that, and separating them by commas and enclosed by this flower bracket. So this is nothing but a roster form. So can you write this the same set in a set builder form? Yes, right. So we can write that what is mean by this? Set of all natural numbers. Set of all natural numbers such that it lies between 2 and 5.
2 and 5.
2, 5. This is nothing but set builder form. A form which we call it as a set builder form. That means what? It is every element that has some property. That means a natural number lying between 2 and 5. This is my property. This is my property. So in which we can represent elements like this. So this we call it as actually what? Set builder form. Right? Suppose you can have another example. Set of all real numbers x square plus 4 is equals to 0. Can you write the elements in a roster form? What is my set?
Yes,
set
sir.
of all real
2
numbers.
comma minus 2.
2 comma minus 2. Sir, minus 2.
Set of all real numbers.
No, no.
No, sir. Does not exist, sir.
Yeah.
Complex number.
Sir, minus 2i.
Plus or minus 2i. There is no real numbers.
Yeah. That means what? You take any real number. Whose square is always non-negative. That means any real number whose square is always non-negative. Therefore, once you add the 4 on both sides, what you get? X square plus 4 is always bigger than equals to 4. 4 is always positive. Therefore, x square plus 4 is positive for any real number. Therefore, there is no such a real number whose square plus 4 is 0. Right? There is no such a real number whose square plus 4 equals to 0. So therefore, there is no element. That means what? It's an empty set. It's an empty set. Right? Suppose same question. Suppose if I given a restriction, set of all complex numbers such that x square plus 4 equals to 0. Yeah, can you write the elements?
Sir, minus 2i.
Yeah, plus or
Plus
minus?
or minus 2i. Plus or minus 2i.
Plus or minus 2i. That means what? Minus 2i plus 2.
Plus 2i.
Right? So this is nothing but what? Roster form. This is nothing but what? Set builder form. Yes or no? This is my set builder form. This is nothing but what? Roster form. This is in roster. This is in set builder form. Right? So this is about we represent the sets in 2 forms. One we call it as roster form. One we call it as set builder form. Next is classification of sets. Classification of sets. So classification of sets according to cardinality is 2 types. So what I mean by Cardinality of the set. First, you need to define a cardinality. So, what do you mean by cardinality of the set?
Number of elements in a set.
Number of elements in the set.
Right.
Number of
Cardinality of set. Just you keep in mind, this is very, very important, but because I'm going to use this concept in countability. So just you keep in mind cardinality of a set. So cardinality of a set is nothing but what? Simply number of elements in a set is simply called as a cardinality of the set. Right. Suppose A is my set. Generally, the cardinality of A is simply denoted by, so there are several notations actually. So you can use this model, or else you can use this model. So cardinality of the set, generally we can use this model, or like this, or n of A, number of elements, right? So these are the ways of representing the cardinality of A, right? Suppose you take my example. Suppose A is equals to, suppose -1 + 1. What is the cardinality of this? Number of elements. How many number of elements? 2. Right? Suppose my set is set of all real numbers such that x square minus 2 equals to 0. What is the cardinality of this?
0, sir.
What is my this? Set of all real numbers such that x square minus 2 equals to 0.
1 cardinal.
2, sir.
2, right? If you take any element, it satisfies x square minus 2 equals to 0. So that means what does mean by this? Actually, the set. What is my set? Actually, my set is nothing but set of all real numbers satisfying x square minus 2 equals to 0. That means what? The element which is in A is nothing but a root of the polynomial x square minus 2. Right? Any element that you take in A, that is always a root of the polynomial x square minus 2 equals to 0. Therefore, you need to find the roots of the polynomial. What is the root of the polynomial? This x is equals to plus or minus root 2. Therefore, what is my A? Minus root 2 plus root 2. So therefore, what is the cardinality of A?
2.
2. What is the cardinality of A?
1.
2.
1.
Suppose you take this. What is the cardinality of A? Minus root 2 plus root 2. Cardinality is 2. Right? Yes or no?
Yes, sir.
Suppose you take set of all real numbers such that x cube equals to 1. What is the cardinality of this? Anybody?
3, sir.
1.
Who said 1? Who said 1?
3, sir.
3 na? Who said 1? ఎవరు 1 చెప్పారు? ఎవరు చెప్పారు? 1 అని ఎవరు
Sir,
చెప్పారు?
1, sir. A cube minus B cube,
One కదా సార్.
1 only.
Yeah,
So
that means
One
okay,
omega,
that means you take any real
One
number.
omega square.
That means this is third roots of unity, right? Third roots of unity. Therefore, the roots are only 1 omega square. You know, these are the complex numbers. But what I am interested, we are interested in only real numbers. Therefore, this such a omega square should not be there in A. Therefore, the only root which is equals to real root is x equals to 1. Therefore, A is equals to only singleton 1. Right? Omega square I don't require because I am interested in only real roots of x cube equals to 1. Therefore, A equals to singleton 1. The cardinality of A equals to 1 itself. Right? Suppose if I take the same question, take the same question with a different restriction, if I take the restriction set of all complex numbers, such that x cube is equals to 1. What is the cardinality now?
3 order is
3, sir.
Yeah, the roots are 1 omega
Omega square.
Therefore, the set is exactly precisely 1 omega square. Therefore, the cardinality of A is equals to 3. Yes or no? Yes, right?
Yes, sir.
Suppose you take the same set, suppose set of all real numbers such that, suppose you take like this, or else you can take like this, set of all complex numbers, set of all real numbers, okay? X square plus 1 equals to 0. What is the cardinality of this?
0.
0. Because it's my empty set, already I told you it's an empty set, cardinality is 0. Right? Suppose you take this set of all real numbers, x square plus 4 equals to 0. What is the cardinality?
Is also 0, sir.
Zero.
Zero, sir.
Suppose you take the set of all complex numbers. Set of all complex numbers.
Two.
Set
Two,
of
sir.
all. Set
Two,
of
sir.
all. Set of all complex number. I'm not completing the question. Set of all complex numbers. Such that x cube plus 4 equals to 0.
3.
Anybody?
One.
Only one?
Sir,
3,
three.
3, 3, sir. 3, sir.
3, sir.
Can you write the elements? A element that you take in A,
One,
that should
sir.
be x cube plus 4 equals to 0. That element you take in this, that x cube plus 4 equals 0. So can you write the elements? Anybody? X cube is equals to minus 4. Because I'm interested in complex numbers, x cube equals to minus 4. So what are the roots? Anybody? What are the roots? Anybody? So 4 power minus 1 by 3, 1 minus 1 whole power 1 by 3. So therefore, what are the roots? 4 power 1 by 3 is nothing but equal 2k pi plus pi divided by 3 into I, where k equals to 0, 1, 2. Right? So therefore, how many roots? For k equals 0, we can have one root. For k equals to 1, we can have another root. For k equals to 2, we can have another root. Therefore, how many roots?
3.
3 roots. Right? So this is being simply called as 3 roots. Right? So that means you take any polynomial in a complex numbers, definitely it has a root by fundamental theorem of algebra. Definitely the coordinate of the set is same as saying that number of roots of such a polynomial for a complex field. Right? So this is nothing but the cardinality of the set. Suppose you take this question, A is equals to suppose 2, 4, 6, 8, 10, 12, 18, 16, 20, 22, like this. What is the coordinate of this?
Infinity.
Infinity, right? Because number of elements is infinity, therefore the coordinate is infinity. In fact, coordinate is here allowed not, we'll see later. So of course, but right now coordinate of is infinity. Okay. So therefore, according to the coordinality, we can classify the sets into two types. One is finite sets. Second is infinite sets. Right? One is finite set. Second is infinite sets. So finite sets means what? Finite sets means a set is said to be finite. So this is very, very important. This is looking like a finite set, simple 10th class, simple intermediate. Don't skip like this, because once you want to define a countability of a set, what remember countability of a set? It is either finite or there is a bijection between the natural numbers to the given set. So finite set is very, very important, plays very, very important role to define a countability of a set. Right? The set is said to be finite if and only if the coordinate is finite. Right? Otherwise, it is infinite set. Right? Example, can you give example? Suppose you take a natural numbers. Is it finite set or infinite set?
Infinite set.
Infinite set. Infinite set. Suppose you take set of all odd numbers.
Infinite.
Infinite only.
Infinite. Suppose you take set of all odd numbers lying between 1 and 7.
Finite.
Finitely, sir. Finite, sir.
Yeah, 6 is an odd lying between 1 and 10, 1 and 11.
Finite set.
Finite.
Finite set. Can you give me 3, 5, 7? Right? What is the cardinality? It's a finite.
Three.
3. Right? So this is about finite sets and infinite sets. Next is finite sets and infinite sets. Next is we define the different types of sets. First one is empty set. Is also one of the definition. What does it mean by empty set? A set which has no elements. A set which has no elements. So means what? You take this as my empty set because it has no elements. right? So of course we can denote this set as this notation, empty set, right? Of course we can write the things like this: set of all real numbers such that you take x square plus 1 equals 0 is also empty set. Of course we can take set of all integers such that x square plus 5 equals to 0. This is also empty set, because there is no such an integer whose square plus 5 equals to 0. Therefore these are the possibility of the empty sets, right? Empty set means what? It has no elements, right? Next is what? Equality of the sets. What do you mean by equality of sets? We say that two sets are equal. So this is also important idea once you go through the countability. So what do you mean by equality of set? Once you take two sets, A and B are equal sets if and only if both are same. We say that two sets are equal if and only if we say that two sets are equal sets. Suppose you take A equals to 1, 2, 3, and we have given actually just now set of all natural numbers, that is less than or equals to x1 less than or equals to x, and lying between 1 to 4 including 1. Set of all natural number lying between 1 and 4 including 1. So what is this my set? My set is set of all natural numbers. This is my 1, 2, 3, 4 going on. So natural numbers. So what I require is set of all natural number lying between 1 and 4 including 1. So lying between 1 and 4 means what? 1, 2, 3, 4 is not included. Therefore 1, 2, 3. Therefore these two sets are equal. Therefore A equals to B. Right? So these two sets are equal sets. Suppose you take these sets. Suppose C is equals to A, B, C. Are they equal sets? No, right?
No.
A cannot be same as saying that C. A cannot be same as saying that C. They are equivalent set. They are not equal sets. Right? They are not equal sets, but they are nothing but what? Equivalent sets. Next is nothing but what? Subset. So what do you mean by subset? Anybody? You take A and B are sets.
Any non-empty set which is contained in the superset.
So you take any two sets. Let us consider A and B are two sets. We say that A is subset B.
If each element of A contained in B.
Yeah, A is a subset of B. If and only if every element of A
Is an element of B.
is an element of B. So in notation we can write like this. A subset means we can write this notation. A subset B means that every element that appeared in A is an element of B. If that happens, we can say that A is subset of B. Right? Suppose we take this. A is equals to 1, 2, 3. Of course 1, 2. What are my subsets? Anybody?
4. 4.
1.
4. 4.
So
4. 4.
One
Sir.
is, yeah, 1 is a subset of A.
2 is a subset.
Singleton 2 also subset of B. A.
1, 2
And
also a
A
subset.
set. A 5.
And
Empty set. Empty set.
right, so empty set is subset of every set, and the set itself is also subset of every set, that itself. Therefore these are my subsets. Suppose you take this, B is equals to, suppose 1, 4. Is it a subset of A?
No.
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 No,
B is
sir.
not subset of A. Right? B is not subset of A. What do you mean by subset of A definition? Any element of A is an element of B. Any element of A is an element of B. See why B is not subset of A?
Order of B is a
Node does not contain the A.
Yeah. What do you mean by A subset B? Any element of A should be element of B. What is the negative of this statement? What is the negative of this statement? We find at least one B, which we call it as B. B is an element of B, but B that 4 is not element
Not
of
an element of A.
right. What is the negative of the statement? What is the statement? This tells you that every element that appeared in A is an element of B. What is the negative of this? There exists at least one element in A which is not an element of B. So what I mean by A is not subset of B means what? There exists at least one element in A such that which does not belongs to
Which is not in
B, right? So this is also important idea. Negative statements plays a very important role in mathematics while proving theorems and problems, right? So this is nothing but a subset, right? What do you mean by superset?
There exists at least one element in B which is not in A. Then B is called a superset of
Yeah.
A.
Suppose I'm going to give a question like this. Suppose, notice, if a set as if A is a set with the cardinality is n, what is the total number of subsets?
2 power n. 2 power n.
2
Two
power
power
of n.
Power n.
Yeah, total number of subsets of A is nothing but what?
2 power n.
2 power n. That means we select none of the elements. That is nothing but select elements. See how many elements we have n elements. We select none of the elements. That is nothing but what? NC0. We select singleton sets. That is nothing but NC1. We select two-ton sets. NC2. We select n-ton sets. That is NCn. Therefore, total number of subsets is nothing but what? NC0 plus NC1 plus NC2 plus NCn. That is exactly binomial theorem. Is nothing but what? 1 plus 1 whole power n. That is nothing but what? 2 power n. Right? So therefore, the cardinality of that means that total number of subsets of A is nothing but what? 2 power n. 2 power n. This is very, very important. Total number of subsets of A is nothing but what? 2 power n. Right? So here, how many subsets you have actually? Pi, singleton 1, singleton 2, 1, 2. So here 1 is 1 comma 2. A set itself is nothing but what? Improper subset. Improper
Yes.
subset. Other than
Pi
this,
also improper.
we can take
No,
in some
proper.
Pi and itself is improper.
in some sense, in some textbook, why pi can be treated as an improper, but most of them pi cannot be treated as a improper set.
Okay, sir.
So A itself is a, in some textbook, pi can be also treated as a improper set, but most of the standard textbooks, pi cannot be treated as a improper set. So therefore, this we call it as improper subsets, and this we call it as actually what? Proper subsets. So therefore,
Proper subsets.
here, this is my first note is, so total number of proper subsets,
2 power n minus 1.
right? That's it. Because the only problem with the set itself, you delete that set, right? By deleting the set itself, so total possibilities are 2 power n, problem with only 1. So total minus problem term means 1. So the 2 power n minus 1. Right? Next is superset. Superset is nothing but what? If you take two sets, A and B are two sets. If A is subset of B, we say that B is a superset of A. That's it. Right? Just you need to know the notion, that's it. But subsets are very important, you know. Of course, once you define a subset, automatically the bigger set is a superset of given subset. That is the notion of this. Right? Next is what? Suppose you take this example. Suppose this A equals to 1, 2, B equals to what? 1, 2, 3, 4. So clearly 1 is here, 2 is here. Therefore, any element of A is an element of B. Therefore, A subset B. Here B is a superset of, B is a superset of
A.
Yes or no? A is a subset of B. We call it as this subset of B. A is a subset of B. B is a superset of A. Right? Next notion is power set. So what do you mean by power set? A set of all
Subsets.
So
Set of all subsets.
Yeah, that's it. You take a set. Let us start with a set. A set of all subsets of a given set of A, simply denoted by In general, standard notation is P of A, right? So set of all subsets of A is nothing but what? Simply the power set of A, right? So notice, first notice, empty set is subset of every set. Yes or no? Because if it is not subset of A, if pi is not subset of A, what happens? There exists at least one element such a way that X does not belong to A, right? This won't happen. So therefore, pi is always subset of A. Pi is always subset of A, right? If it is not subset of A, automatically we find the element pi in pi such that which is not a member of A. So this won't happen. Therefore, pi is a subset of A, and a set is always subset of itself. To take any set, right? So therefore, let me give an example of a power set. Suppose you take A equals to 1, 2, 3. So what are the subsets now? Empty is always subset of, and A is a subset of A, and singletons and 2 tons. Yes or no? 2 tons and 3 tons. 3 ton is nothing but what? Set itself. So total how many subsets? 8 subsets. If you these elements are enclosed by a floor bracket, this set is nothing but a power set.
Okay.
If you enclose these elements by a floor bracket, by writing elements commas, by writing the elements by commas, separating the elements by commas, particular commas, we say that this is a power set. So what is the coordinate of power set?
2 power n.
2 power n.
Right? What is the coordinate of the power set minus set itself?
2 power n minus 1.
2 power n minus 1. That's it. A deleted. Yes or no? This is set difference. We'll say later. So this is 2 power n minus 1. What is the coordinate of the power set minus singleton 1?
2 power n minus
1. Because
1.
deleting this set itself. 1. Right? This is about power set. Power set is nothing but what? A set of all subsets of the given set. Right? This is also very, very important because there is a Cantor's theorem. There is no bijection between A and its power set. So this is also important concept while defining the countability of a given set. Right? Next is universal set. What do you mean by universal set? Anybody? A set under consideration containing all subsets. Yes or no? A set under consideration means under some restriction, right? With all subsets, containing all subsets, containing subsets is called universal set. Right? Simply denoted by, there are so many letters. You can use mu or this notation. Right? Suppose let me give an example. Suppose my Shatavan University there. This is my university. Right? We have a department of mathematics, department of chemistry, department of English, department of Telugu, department of right, like political science, department of like MBA, commerce, business management. So these are nothing but elements in Shatavana University. Yes or no? So this department of mathematics is always a subset of Shatavana University. It's also subset of Shatavana University. It's also subset of Shatavana University. It's also subset of Shatavana University. So every member which appeared in Shatavana University is a subset of the Shatavana University. Therefore, this we call it as a universal set. So what is my universal set? Means nothing but a set under consideration containing all subsets is nothing but universal set. Right? So universal set is nothing but what? It's denoted by mu letter. Right? So this plays also very, very important role. Right? Next is operations. Operations. What are operations? So one is unions, set unions. One is intersections.
Functions.
One is So difference. One is symmetric difference. Right? So union generally we use this notation, the cup symbol in LaTeX. This is intersection notion. This is symmetric. This is nothing but set difference. In some books, A minus B, we denote it like this. In some standard textbook, we can use the slash notation. This is my set difference notation. Right? So what do you mean by union? Suppose you can have two sets.
Combining the elements of A and B.
Right. The set of all elements of A and B. Right?
Yes.
So that means what? Union of these two sets. So denoted by this A union B. What is my definition of A union B? A set of all elements such that either in A or B. A set of all possible elements in A and B is nothing but what? A union B. Right? Suppose you take this A equals to 1, 2. Suppose you take B equals to AB. What is A union B?
Set A.
1, 2, AB. That's it. Just writing the all elements appeared in A and B. Nothing but what? Set of all elements in A or B. Right? A or B. A lo unna palle, B lo unna palle, rendu combine chesi rastaru. That is nothing but your A union B. Right? Next is, suppose you take this intersections. What is intersection? Suppose you take two sets.
Common elements.
So A intersection B is denoted by like this: a set of all elements which belong to
A and B.
A and B.
which belong to A and B. That notation is set of all elements such that X is in A as well as
A intersection
B. So in Venn diagrams, in unions, we can represent like this. This is my universal set. You can take this as a universal set. Suppose you can take this my A set. Suppose this is my B set. What is A and B? Set of all elements in A or B. This is my Venn diagram about A and B. Right? Set of all elements in A as well as in B. So this is my A and B. Right? So what is my intersection B? Suppose you write the elements like this: A equals to B, B equals to A, comma B. What is the intersection B?
empty set.
Empty set.
We don't have any common element, so it's an empty set. So can you write the element? Can you write the sets in a Venn diagram? Yes. They are separated. They may not intersect. Yes, I know. This is my 1. This is my 2. This is my A. This is my B. This is my A. This is my B set. This is my universal set. Therefore, they cannot intersect because they don't have a common element. Therefore, the Venn diagram we can represent the two sets like this, separate by two circles. This is one my set. This is my B set. They do not intersect because they don't have a common element. Right? Suppose if I restrict the condition, the same example, if I take like this, B is equals to 1. Right? What is the intersection B?
1, sir.
1.
We can have only one common element. So that is nothing but only 1. So we can represent these two sets by like this. So 1 is here. So A contains two elements. 1 is here, 1 is in common. First you fix in the common. This is my common region. Right? First you fix one element in the common region. And A contains two elements, 1 and 2. So you fix 2 in A. And this is my B. B as it is, B contains 1. So this is my Venn diagram about intersection B. Right? So this is my intersection B. Next is disjoint sets.
Sir, A contain totally elements of B, sir.
A contains total set of A contains B total.
So Venn diagram should be
one of them. One it should be like
inner circle of A.
Of course. It contains that.
There is no other elements in B of A.
So therefore A is a big set. B is my small set. Of course. Very good. So A contains total B. A contains total B. So this is my Venn diagram about this. But in fact, actually, A intersection B is nothing but B itself. In fact, what is my intersection B? My intersection B is only B. Yes or no? Only B. This is my intersection B. Because A intersection B is itself B. Right? So suppose you take this disjoint set. Disjoint set.
A intersection B.
A intersection B is equal to 5.
Right. A and B are sets are disjoint sets.
Two sets.
Disjoint sets. If and only if they don't have a common element. They don't have a common element. What is the Venn diagram? They do not
Separated by two
intersect.
sets.
They do not intersect. Right? So these are nothing but disjoint sets. Suppose you take my set like this, 1, 2, B is equals to set is my like this A, comma B. Are they disjoint?
Yes, sir.
Yes, because A intersection B is an empty. Therefore, they are disjoint sets. They are disjoint sets. Is it clear? Yes. Is it clear, Andy? Yes. Right. Suppose you take the another example. A is equals to 1, 2. B is equals to 2. Are they disjoint?
No, sir.
No, sir.
The intersection B is 2. Which is not empty. Therefore, they cannot be disjointed. They cannot be disjointed. Now, third one, the difference. What is the difference? You take two sets, right? You take two sets. What is the difference?
Sir, X belongs to A and X does not belongs to B.
Yeah, set difference of A and B denoted by this notation means the elements which appeared in A but not in
B.
Yeah, set of all elements
Belongs to only A.
in A but not in B. So in notation, A minus B is simply defined by set of all elements in A but not in B. But not in B. Yes or no? So therefore, suppose you take this example, A is equals to 1, 2, B is equals to 1, 3, 4. What is A minus B? So 1, 2 minus 3, 4. So
1,
elements
2,
which
sir.
are in A, 1 is an element in A but not in B. Okay. 2 is an element of A but not in B.
Yes, sir. 1, 2.
So,
Sir.
yeah, this only. Right? Suppose you take this, A is equals to 1, 2, B is equals to just 1 itself. What is A minus B?
2, element 2.
Yeah,
Sir, 2.
Sir.
only 2, right? 2 is in
Only 2,
A
sir.
but not in this. Therefore, A minus B is this. So can you write the Venn diagram? So there are two possibilities for Venn diagram. If A intersection B is an empty, we can have one Venn diagram. If A intersection B is non-empty, we can have another Venn diagram. If A intersection B is an empty, what is A minus B? This is my A minus B. A minus B is nothing but exactly A itself. We have seen just now. If A intersection B is here, actually A intersection B is empty set. Therefore, A minus B, you have seen that it's an A itself. Therefore, my Venn diagram is itself is A. If A intersection B is non-empty, that means they are overlapping sets. They are intersecting sets. What is my A minus B?
Except
The set of elements
common
which are in
variance.
A, the
Yes, sir.
elements in A but not in B. Right? So this is my A minus B. Right? Next is what? Difference. Means next. What is that? Symmetric difference. Previous one set difference. This is symmetric difference. So this plays very, very important role while in group theory and vector spaces. Right? Set of all. So that means what is meant by symmetric difference? You can take two sets. What is set difference? Symmetric difference? Symmetric difference
Minus B union B minus B.
denoted by
A delta B.
A delta B is defined by like this. What is A delta B?
A union B minus A intersection B.
Yeah, A union B minus A intersection
A
B.
intersection.
Or else
A minus B union B minus A.
union B minus
B minus A. Right? Suppose they are overlapping sets. Okay. You need to give a counter. First, you need to take an example. 1, 2. For understanding purpose, I am taking two simple sets. So suppose you take A1, B A comma 1. So what is A minus A delta B? So A minus B means what? 1 is there, 1 is there. A minus B means 2. A minus B means what? 2 union B minus A. A. The elements which are in B but not in A. Therefore, A only. Therefore, A minus B. What is A minus B? First of all, A minus B is nothing but what? Only 2. The elements which are in A but not in A. 2 is the only element which is appeared in A but not in B. What is B minus A? Yeah, what is B minus A? The element we only A which is appeared in B but not in A.
A.
So this is my
A, sir,
A.
I'm
So what is
alternate,
A delta B? What is A delta B?
2A.
Yeah, by definition,
Two
it is
A.
nothing but what? A minus B union B minus A. Therefore, 2 union A. Therefore, 2 comma A. This is A delta B. Right? So, you can write the symmetric difference. We have defined the symmetric difference also. Right? In Venn diagrams, suppose there are two possibilities. They are overlapping sets. What is A delta B? Anybody? A minus B union B minus A. This is A minus B union B minus A. B minus A is nothing but this. So this is my Venn diagram about whenever A intersection B is non-empty, because they are overlapping sets. Suppose you have a two sets which are disjoint sets. A intersection B is an empty case, right? So what is meant by A delta B? Simply A minus B means total A. B minus A is total B. So this is my A union B, right? So this is an example of this, right? And next properties. Right. So first one, A union satisfies idempotent property. A union A is equals to A, and intersection satisfies idempotent property. A intersection A is equals to A,
A.
and
Yes, sir.
this is nothing but idempotent laws. Right. Next, union satisfies. Union is committed to A union B is equals to B union A, and intersection also committed to A intersection B is equals to B intersection A. Right. Third one is union is associative. Intersection also associative. Next is union is distributive over intersection. These are nothing but associative clause. You should keep in mind these are very, very important once we go through the ring theory and group theory. This A union B intersection with A union C. So and intersection also distributive over union. This A intersection B union intersection C. This is left distributive. This is also left distributive. Of course, you can write right distributive also. It's nothing but what? B union A intersection with C union A. This is nothing but what? Like same thing, right distributive. So B intersection A union with C intersection A. These are nothing but what? Distributive properties. Next is, De Morgan's. These are very, very important once you go through the analysis, so that I'm giving the basics. Suppose A and B are two sets. A intersection B whole complement. See, complement of the intersection is nothing but union of the complements. Union of the complements. Of course, complement of the union is nothing but intersection of the complements. Of course, not only this is true for two sets, this is true for any countable, uncountable collection. You can take any arbitrary collection, you take the complement of the union is nothing but intersection of the complements. You can take any collection, not only two sets, You can take any arbitrary collection. You can take any arbitrary collection. Right? These are nothing but what? De Morgan laws. These are nothing but what? De Morgan laws. Next is, you know, 6 A complement, whole complement is nothing but A itself. A complement, whole complement is nothing but what? A itself. And you can have another A in A complement is nothing but universal sets. Right? So these are the very, very important properties once you go through the